Welcome back, Design Junkies. We are Mechanical Engineering Made Simple, Thermodynamics Lesson Time 1 of 5. Schools teach it like it's all clean formulas that always work out, that you get it on the shop floor and it burns your ass in ways the book never mentioned. Marcus Aurelius said, "You have power over your mind, not outside events. Realize this, and you will find strength." He doesn't care about your numbers. Learn how it works or keep fixing broken parts. Let's get into it.
Yeah, that quote is just, it's the perfect anchor for what we're breaking down today. Because, the mathematical models you learn in university, they're essential, obviously, but they represent this perfectly idealized version of reality.
Right. A totally clean reality.
Exactly. They assume a universe with no friction, no microscopic imperfections, and absolutely none of the chaotic, turbulent nature of real fluid dynamics.
Yeah, which is just wild when you think about it.
It is. And understanding the assumptions hiding behind those clean equations, well, that's literally the only thing that saves a multi-million-dollar project from just catastrophically failing on the floor.
So, okay, consider this your unvarnished masterclass.
Yeah.
Because, everyone passed Thermodynamics 101.
Hopefully.
Right, hopefully.
Right.
We all know energy is conserved, right? That's day one stuff. But the disconnect happens when you take a perfect, idealized textbook formula and you actually expect your physical machine to deliver it without any consequence.
Right, without paying the tax.
Exactly, the tax. So our mission for this deep dive is to give you, the young engineer, staring down some massive complex system, the factual, unvarnished truth. We're breaking down how mass flow, turbo machinery efficiencies, joint resistance, and thermal expansion actually behave.
No pre-promises.
No pretty promises at all.
Yeah.
We are bridging that gap between the clean whiteboards academia and the brutal, unforgiving reality of the shop floor.
And honestly, it is the most vital transition you'll make in your entire career. Moving from, just passing an exam to actually keeping a machine from vibrating itself to pieces.
So before we can even talk about machines melting down or, ripping their own welds apart, we got to establish the absolute baseline, right? We have to look at the gatekeepers of physical reality.
The foundational rules.
Right. How fluid and energy actually move through any system. Because if you don't understand the baseline, you can never, ever identify the anomaly.
That's right. And that primary baseline, it starts with the physical conservation of mass. So in fluid mechanics, we rely on the continuity of flow equation.
Yeah, lay it on me.
Well, in most introductory analyses and, in the initial design phases of any fluid system, we limit ourselves to one-dimensional steady flows.
One-dimensional steady flows. Oh.
Right. This basically assumes a system where the velocity and the fluid density are just regarded as constant across each section of a duct or a passage.
Let's translate that math into a physical mechanism, though. Because, textbooks love to just list variables, right? Like m dot rho, CA, and then they just leave it at that.
They really do.
So think of the continuity equation as like a strict bouncer at a nightclub. The physical matter of your fluid, it cannot magically appear out of nowhere, and it definitely cannot vanish into thin air.
It has to go somewhere.
Exactly. So the total mass moving through your system per unit of time, which is your mass flow rate, is an absolute bottleneck. The equation is m dot equals rho 1 times Cn1 times A1. And that has to perfectly equal rho 2 times Cn2 times A2 at the exit.
That's the one.
So it's dictated by the density of the fluid, multiplied by the speed that the fluid is moving straight through the pipe, multiplied by the cross-sectional area.
And that directionality, that is the part that often gets totally overlooked in initial designs.
How so?
Well, when we talk about the velocity of the fluid in this context, the Cn1, we are strictly talking about the component of the stream velocity that is perfectly perpendicular to the cross-sectional area. The N stands for normal.
Oh, right. Normal to the plane.
Exactly. So if your fluid is swirling or hitting the cross-section at an angle, you only count the vector of the flow that is moving directly through the plane.
So all that sideways energy doesn't count for the mass flow rate.
It doesn't. If you have a massive pipe, but the flow is entirely turbulent and it's just hitting the walls at severe angles, your effective forward velocity is actually just a fraction of the total fluid speed.
Wow. Okay, so that total mass flow at the entrance, it has to be exactly the same as the mass flow at the exit. The bouncer counts 10 people in, 10 people have to come out.
Perfect analogy.
And that conservation of mass, it perfectly sets up the first law of thermodynamics, right? Which is the conservation of energy.
Yes, the fundamental law.
You take a system through a complete cycle, heat is supplied, work is done, but the energy ledger always balances. Always.
It does. Every thermodynamic equation is essentially an accounting ledger. For a tiny infinitesimal change, The math is dE equals dQ minus dW.
Meaning the change in the internal energy of any system is exactly equal to the heat supplied to the system minus the physical work done by the system.
Exactly. Heat in minus work out equals the change in the internal energy. But when we apply this to a continuous flow of fluid through a machine, like a massive gas turbine or a big industrial pump, we can't just use that simple version.
Right, because the fluid is moving.
Yeah, so we use the steady flow energy equation for a control volume.
And this is where the textbook math usually trips people up, right?
Yeah.
Because it's not just tracking the heat transferring through the metal casing or the work twisting the physical shaft. You actually have to account for the physical state of the fluid itself.
You do. You have to track its specific enthalpy.
Which is H.
Right,
Yeah.
and you have to track its kinetic energy based on how fast it's moving, and even its potential energy based on gravity.
So the full equation is Q dot minus W dot X equals M dot multiplied by the sum of a few things, right?
Yeah. Yes. It's m dot multiplied by the sum of the change in enthalpy, so H2 minus H1, plus the change in kinetic energy, which is 1/2 times the difference of C2 squared and C1 squared.
The velocities.
Exactly. And finally, plus the change in potential energy, which is G times the difference of Z2 and Z1.
Okay, but honestly, unless we are talking about like a massive hydroelectric dam with a huge elevation drop, gravity is basically a rounding error, right? We just ignore it in gas turbines.
Oh yeah, it is entirely negligible in a gas turbine. The difference in elevation between the inlet and outlet simply does not register compared to the massive thermal and kinetic energies involved in the gas expansion.
It's just a drop in the bucket.
Barely even a drop. So the steady flow energy equation, it forces you to account for the rate of heat transfer from the surroundings, the rate of mechanical shaft work being done, and the mass flow rate carrying that enthalpy and kinetic energy.
But okay, wait. I have to push back here because this is the exact frustration young engineers face on the floor. We just established that real-world flow is chaotic, right? It's turbulent, it bounces off the walls, it creates eddies and vortices. So why do the textbooks and honestly the initial design softwares, why do they insist on this one-dimensional steady flow model?
That's a very fair question.
Is this just academics being lazy because the turbulent math is too hard to solve by hand? Or is there like an actual practical shop floor reason you would use this perfectly idealized math?
Oh, it is absolutely not laziness. It is about establishing a rigorous, unbreakable theoretical limit.
Okay, how so?
The steady flow model is your sanity check. It represents the best case scenario for efficiency and the worst case scenario for energy requirements. Think of it as the ultimate gatekeeper for your design.
Like a filter.
Exactly. If your proposed compressor fails to balance the one-dimensional steady flow math on paper, like if the idealized equation says you need 500 kilowatts of power to achieve a certain pressure ratio, but your motor is only rated for 450 kilowatts.
Then you're already dead in the water.
You do not need to run a complex, three-dimensional, turbulent, computational fluid dynamics simulation to know your machine will fail.
Wow. It's dead on arrival. If your machine can't survive the perfectly idealized mathematical world, it will be instantly destroyed by the turbulent reality of the physical world.
Precisely the point. You use these idealized equations to establish the theoretical maximums and minimums of what is physically possible.
That makes total sense.
Once you know that your design survives the baseline energy conservation check, well, then you can look at what happens when we force that fluid to actually do something useful.
Right. Which means moving from the abstract concept of conserved energy into the physical reality of moving machinery. We're putting the fluid to work.
We are.
We're smacking that high-velocity gas into a spinning turbine blade. And to measure that, we have to look at how energy transforms.
In turbomachinery, we're dealing with fluids moving at incredibly high velocities. The specific enthalpy of the fluid, its internal thermal energy and flow work. That's only half the story.
Because it's moving so fast.
Right. We have to account for the kinetic energy. So we use a combined property called stagnation enthalpy.
And the math for that is H naught equals H plus 1/2 C squared.
Yes, exactly.
I got to say, I love the visual for stagnation enthalpy because the textbook definition is that it combines specific enthalpy with the kinetic energy of the fluid per unit mass. But the physical translation is so much more visceral than that.
It really is.
It's essentially asking the question, if I threw an indestructible, invisible brick wall in front of this high-speed gas flow and forced it to come to a violent, immediate halt, without losing heat to the surroundings, what is the absolute total energy it possesses in that static moment?
The brick wall analogy accurately captures the conversion. You are taking all of that forward kinetic velocity and mathematically converting it back into internal thermal energy and pressure.
It just turns into pure heat and pressure.
Exactly. It is the absolute total energetic potential of the fluid stream. And the reason we track stagnation enthalpy so closely is that flow processes inside turbomachinery happen incredibly fast. I mean, the gas rips through a turbine stage in fractions of a second.
Meaning there is literally no time for the heat to escape through the heavy metal casing into the factory air.
Exactly. The process is essentially adiabatic, so if there is no heat escaping, the mathematical ledger simplifies beautifully.
Which is always nice.
Very nice. For a work-producing machine, like a steam turbine, the mechanical work you get out of the shaft is strictly equal to the mass flow rate multiplied by the drop in the fluid stagnation enthalpy from the inlet to the exhaust.
And for a compressor.
For a compressor, the electrical work you pump into the motor equals the rise in the fluid stagnation enthalpy. The stagnation enthalpy tracks exactly how much energy was transferred between the fluid and the spinning blades.
But, okay, how does that energy actually transfer? Like, a drop in enthalpy is a thermodynamic concept. A spinning steel shaft is a mechanical reality. How do we bridge that gap between temperature and pressure and physical torque on a shaft?
We bridge that gap using Euler's equations of motion.
Okay, Euler.
Yeah, which are derived directly from Newton's second law. In a rotating machine, the sum of the moments of the external forces equals the net time rate of change of angular momentum.
Okay, break that down for me.
We look at the blade speed, which we call u, and u equals omega times r, so the angular velocity of the rotor multiplied by its radius.
Right.
And then we look at the tangential component of the fluid's velocity, which is c theta. This is how fast the fluid is swirling around the axis of rotation rather than just moving straight through the machine.
So is that swirling motion?
Exactly. And Euler's pump equation puts it all together. The specific work, delta WC, equals U2 times C theta 2 minus U1 times C theta 1.
So Euler's pump equation is essentially telling us that the specific work done on the fluid, the actual physical energy injected into it, is purely a function of how fast the metal blades are spinning and how much tangential swirl those blades impart to the fluid between the inlet and the outlet.
Yes, that is exactly it. You multiply the blade speed by the fluid's tangential velocity at the exit and subtract the product of the blade speed and tangential velocity at the inlet.
That's the difference in momentum.
And that change in momentum is the physical torque applied to the shaft. It is an incredibly elegant conversion of mechanics into thermodynamics.
It is elegant, for sure. But when you combine the thermodynamic energy equations with Euler's momentum equations, you get a property that absolutely breaks the brains of young engineers.
Oh, I know exactly where you're going.
Yeah, that property is Rothalpy.
Rothalpy, or rotational stagnation enthalpy. It is a profound fluid mechanical property.
It really is.
If we take the specific work from Euler's equation and set it equal to the change in stagnation enthalpy, we can actually rearrange the variables, and we find this amazing constant.
The equation is I equals H plus 1/2 C squared minus U times C theta, right?
Yes. So the fluid's specific enthalpy plus its kinetic energy minus the product of the blade speed and the fluid's tangential velocity. That creates a mathematical expression that remains perfectly constant from the moment the fluid enters the spinning impeller to the moment it leaves.
Okay, let me try to put a real-world analogy on this, because visualizing a rotating frame of reference is notoriously difficult for people to picture.
It is very non-intuitive.
Right. So I look at Rothalpy like a bank account balance during a chaotic high-speed international currency exchange.
Okay, I like where this is going.
Imagine you are running through an airport. The specific enthalpy of the fluid, your H, that's your cash in US dollars. The kinetic energy, the pure velocity, that's your cash in euros. And the rotational energy, that physical swirling momentum imparted by the spinning impeller, the U times C theta, that is a fluctuating fee you owe in Japanese yen.
And the proportions are constantly shifting as you move.
Exactly. As the fluid molecule rips through the complex twisting geometry of a centrifugal compressor blade, it is constantly exchanging those currencies. It's speeding up, so it's buying euros. It's compressing and heating up, so it's acquiring dollars.
Right, and it's moving further out along the radius of the spinning wheel.
Right, so its yen debt is skyrocketing. It is absolute chaos. But if you were to freeze time at any microscopic point along that flow path and convert all three of those distinct energies into a single base value, that total net worth remains exactly the same.
It perfectly balances.
The currencies constantly change form, but the total balance, your enthalpy, never fluctuates.
That analogy captures the exact utility of the property. When you are analyzing flow inside a spinning rotor, your coordinate system is literally rotating with the blades.
Which is a nightmare.
It is a mathematical nightmare to track. You have centrifugal forces pushing the fluid outward and Coriolis forces twisting it sideways. Enthalpy gives the engineer an anchor point.
A solid number to hold on to.
Yes. It is a constant value along the flow lines that actually survives the dynamic, rotating environment. It proves that even in the chaotic swirl of a jet engine turbine, the fundamental ledger of energy remains perfectly balanced.
But here's the massive pain point. And honestly, this is the exact reason we are doing this deep dive.
The disconnect.
The disconnect. A young engineer looks at the textbook. They see Euler's elegantly simple momentum equations. They see the perfect conservation of enthalpy. They design a centrifugal pump. They calculate the specific work output, and they promise the client this machine will deliver exactly 500 kilowatts of pressure energy to your pipeline.
Yeah.
And then they build it, they put it on the test stand, and it only delivers 410 kilowatts.
Yeah. Happens all the time.
Where is the disconnect? Why did the math lie to them?
The math did not lie. The engineer simply ignored the universe's ultimate tax collector.
The tax collector.
Everything we just discussed. The first law, the conservation of energy, Euler's ideal work. It all assumes a perfectly reversible, frictionless process. It completely ignores the second law of thermodynamics.
And the second law is the harsh truth of the shop floor.
It is.
You never, ever get out what you put in.
Never. The second law dictates the irreversibility of all processes that occur in nature. For closed systems, it says the cyclic integral of dq over t is less than or equal to 0.
Meaning for reversible processes, it equals 0. But for real, irreversible processes, it's always less than 0.
Exactly. It is the fundamental reason we cannot extract the theoretical maximum work from our fuel sources and why we cannot convert mechanical work back into pressure without a massive penalty.
So let's break down how that penalty is actually enforced, because the textbooks introduce the concept of entropy. ds equals dqr divided by t.
Right.
And in a perfectly ideal, frictionless, reversible world, the entropy of a system undergoing an adiabatic process remains constant.
But we do not live in that world. In any real open system, like our industrial pump or gas turbine, we have irreversibilities.
Friction.
Yes, microscopic friction between the fluid and the metal casing. We have internal fluid shear. We have turbulence, chaotic eddies, and shock waves in high-speed flows. All of these physical realities act as irreversible energy sinks.
They just bleed energy.
They do. And because of them, entropy is actively created within the machine. We call this entropy generation, or S-gen. The second law of thermodynamics strictly mandates that S-gen must always be greater than 0 in a real process. You can never destroy entropy, you can only create it.
So entropy only goes up.
Always. And this directly impacts our young engineers' perfectly calculated pump work. To calculate the exact cost of that entropy, we use the Gouy-Stodola theorem.
Oh, so the Gouy-Stodola theorem. That is the ultimate reality check.
It really is.
And it states that the lost work in your system, the energy you permanently lose the ability to use, is strictly equal to the ambient absolute temperature multiplied by the entropy generation, S-gen. So W lost equals T naught times S-gen.
It quantifies the concept of exergy destruction. It tells you exactly how much of your theoretical mechanical power was permanently converted into useless, unrecoverable forms of energy.
So basically, entropy is the mob, and S-gen is the protection money.
That's a very vivid way to put it.
Think about it. You design a business, your pump, and you calculate your theoretical revenue based on Euler's ideal equations. You think you're going to make 500 kilowatts of profit.
Right.
But you are operating in the real physical world, which is run by the universe's mob boss, entropy. And the Gouy-Stodola theorem is the mathematical shakedown.
The shakedown, exactly.
It explicitly states that for every single bit of turbulence in your pipe, for every microscopic imperfection in your ball bearings, for every chaotic swirl of fluid mixing, you are racking up S-gen. And the mob demands their cut off the top.
They do not negotiate.
No. The lost work is the protection money you have to pay out of your total energy budget. You were never operating at 100% efficiency because the physics of the universe literally demand a massive cut of your power.
When you phrase it as a tax, the physical symptoms of a machine make perfect sense.
Right, because you can actually feel it.
You can. When you stand on the shop floor and put your hand on the heavy steel casing of an industrial air compressor, and it feels burning hot to the touch. When you feel the concrete floor vibrating under your boots. When the noise of the plant room requires double hearing protection, you are physically experiencing entropy generation.
Wow.
All of that heat, all of that vibration, all of that deafening acoustic energy, that is power that was supposed to be converted into useful pressure for your pipeline. But it was diverted by friction and turbulence into useless internal energy. It is exergy destruction happening right in front of your eyes.
That's terrifying and awesome at the same time. So if Euler's equations give us the dream, and the second law gives us the mob tax, how do engineers actually account for this when writing a contract? How do we calculate the reality?
Yeah. We survive the reality through the rigorous, unforgiving definition of efficiency metrics. We mathematically compare the ideal thermodynamic changes we wanted to achieve against the actual measured changes we observed on the test stand.
Which seems straightforward.
It does, but this is where millions of dollars are lost through sheer accounting incompetence.
Let's talk about the accounting fraud of engineering. Because of the entropy tax we just established, we have to track our lost energy. The literature is full of different efficiency definitions.
Many definitions. Overall efficiency, eta naught. Mechanical efficiency, eta m, isentropic, or hydraulic efficiency, eta c or eta h.
Right. And you have mechanical losses, power lost between the turbine rotor and the output shaft coupling, just due to friction at bearings and glands, which, can be 5% in small machines, maybe 1% in large ones.
Correct.
But the trap that catches young engineers, the mistake that leads to massive lawsuits and ripped-up contracts, is the difference between total-to-total efficiency and total-to-static efficiency.
This is a critical distinction. It dictates how you view the energy leaving your machine.
Break it down for me.
Let's examine the underlying physics. In turbo machinery, total efficiency, eta TT, evaluates the actual enthalpy drop across the turbine against the ideal isentropic enthalpy drop. But crucially, it uses stagnation enthalpy for both the inlet and the exit values.
Right. And remember, stagnation enthalpy includes the kinetic energy, the sheer velocity of the fluid.
Exactly. By using stagnation properties at the exit, total-to-total efficiency makes a massive assumption. It assumes that the kinetic energy of the fluid leaving the exhaust pipe is still considered useful energy.
It implies that you, the engineer, are going to capture that high-speed exhaust flow and use its momentum for a secondary purpose.
Yes.
Which makes perfect sense in a jet engine. I mean, in a military fighter jet, the turbine's job is to extract just enough shaft power to run the compressor and then blast the rest of the high-velocity gas out the back as thrust.
The thrust is the goal.
Right. That exhaust kinetic energy is highly useful. It's the whole point of the engine. Or, if you have a multi-stage steam turbine, the high-speed steam leaving stage 1 is immediately slammed into stage 2. The kinetic energy is preserved and utilized.
In those specific applications, total-to-total efficiency is the correct, truthful metric. But what happens when that is not the case?
Right.
What happens when you are designing a standalone industrial exhaust fan or a single-stage gas expander, and the fluid leaving the machine is just dumped straight out of a vent into the open atmosphere?
If that exhaust blasts into the open air of a parking lot, that kinetic energy is entirely wasted. It is gone.
Completely useless.
It is useless to the client. And if it's useless, you cannot take credit for it in your math. This is where you must use total to static efficiency.
Let's look at how the math penalizes you here. Total to static efficiency, eta TS, compares the actual stagnation enthalpy drop against an ideal drop down to the static enthalpy of the exhaust.
Not the stagnation enthalpy.
Right, not stagnation. So eta TS equals the difference between H01 and H02, divided by the difference between H01 and H2S.
So the denominator changes.
Exactly. In the denominator, which is the theoretical maximum work you are dividing by, we are no longer allowing the fluid to keep its exit kinetic energy. We are evaluating your turbine's performance against a theoretical machine that extracts every single drop of energy, bringing the exhaust fluid to a complete static halt.
Okay, let's walk through a real-world disaster scenario to show exactly how this accounting error destroys a project.
Let's do it.
Let's say an engineer is hired to design a massive exhaust fan for a mining operation. They run the numbers, they look at the pressure drop, they look at the flow rate, and they calculate the efficiency using the total-to-total formula. They include the kinetic energy of the air blasting out the top of the exhaust stack.
A classic mistake.
Right. The math spits out an efficiency of 88%. The engineer writes a contract promising the mining company a fan that will effectively move air using only 100 kilowatts of electrical power.
A very standard contractual guarantee.
But the engineer forgot that the air leaving the exhaust stack is just blowing into the sky. That kinetic energy is doing zero useful work for the mine's ventilation system. It is pure waste.
Total waste.
So they build a fan, they install it at the mine, and they turn it on. But to actually move the required volume of air, the motor has to draw 115 kilowatts of power, not 100.
Because the true metric, the total to static efficiency, was likely closer to 75%. The kinetic energy they claimed as useful in their spreadsheet was physically lost to the atmosphere.
It just floated away.
It did. And now the machine drastically underperforms the contract specifications, the client's electrical costs skyrocket, and the engineering firm is legally liable for the difference.
All because a young engineer used the wrong column in their thermodynamic tables.
If your exhaust is wasted, your kinetic energy is gone. End of story.
It is a brutal lesson to learn during a lawsuit. The universe's physical mob tax is one thing, but lying to yourself with the wrong efficiency formula is another. You have to trace exactly where every joule of energy is physically going.
And tracing that energy becomes exponentially more difficult when we stop looking at massive megawatt-scale turbines and zoom into the microscopic level.
Right, scaling down.
The fundamental laws of thermodynamics do not change, but the failure modes transform entirely.
Let's zoom in then. We've talked about huge volumes of gas flowing through heavy machinery. But what happens when heat gets trapped on a microscopic scale? We are talking about delicate electronic equipment, high-performance avionics, encapsulated silicon chips.
It's a completely different battlefield.
In turbomachinery, we want to convert heat into work.
Yeah.
In electronics, heat is the enemy. It is a useless byproduct of electrical resistance, and the entire engineering goal is to desperately pump it away before the silicon melts.
The challenge in electronics cooling, especially in harsh environments like aerospace or military applications, is that the operating conditions are rarely steady.
They fluctuate.
Wildly. A satellite passes from the freezing shadow of the Earth into the blazing radiation of the sun. A fighter jet's radar system goes from standby mode to maximum power in seconds. These components experience massive temporal temperature variations.
The temperature is cycling wildly over time.
Yes.
Yeah.
And predicting the failure rates of these microscopic components, the die-attach bonds, the microscopic wire bonds, the solder bumps, it requires understanding exactly how the heat moves through the solid structure of the chip during these transient spikes.
And to model this, we use a dimensionless quantity called the Biot number.
We do.
The Biot number is essentially a mathematical tug of war. The formula is internal conduction resistance divided by external surface convection resistance, or Bi equals L over Ka divided by 1 over Ha.
To understand the physical meaning, let's look at the parameters. It is comparing the thermal conductivity of the solid material itself, how easily heat travels through the metal or silicon, against the heat transfer coefficient at the external surface, how easily heat can escape from the surface into the surrounding air or cooling fluid.
Okay, so if the inside of the chip is like a fast multi-lane highway for heat, but the surface is a massive traffic jam where the heat can't escape into the air, that is a low Biot number.
Exactly. The critical threshold in thermal engineering is a Biot number of 0.1.
0.1.
Right. If your calculated Biot number is less than 0.1, the internal resistance is so small compared to the surface resistance that it is considered negligible. The heat redistributes itself throughout the solid object almost instantly.
So it's basically the same temperature everywhere inside.
Yes. Therefore, we can use the lumped capacity approximation. We can assume the entire solid object has a uniform, homogeneous temperature throughout its entire volume at any given millisecond. The whole chip heats up and cools down evenly as one single lump.
Which makes the math a dream, right? You don't have to calculate complex 3D internal temperature gradients.
But if the Biot number is greater than 0.1, you lose that luxury entirely. It means the heat cannot travel through the solid fast enough to equalize. The outside surface of the chip might be cooling off rapidly because of a fan, but the core of the silicon die is still roasting.
Trapping the heat.
Yes. This creates massive internal temperature gradients, which in turn creates severe internal mechanical stress.
And that internal stress is magnified by one of the biggest, most destructive misconceptions in modern CAD design: the myth of the perfect joint.
Ah, yes. the perfect joint.
This brings us to thermal spreading and contact resistances.
When a young engineer models a heat sink attached to a processor in their CAD software, they define a perfectly flush, mathematically flat plane where the two components meet.
It looks beautiful on the screen.
It does. The software assumes 100% perfect thermal conduction across that boundary. It assumes a flawless pathway for the heat to escape.
But the physical reality of the shop floor is microscopic chaos. If you take those two perfectly machined pieces of metal and look at them under a microscope, they do not look flat.
Not at all.
The surfaces look like the jagged peaks of the Rocky Mountains. They are covered in microscopic roughness called asperities. When you physically bolt that heat sink to the chip, the metals only actually touch at the very highest tips of those microscopic mountain peaks.
The actual area of physical metal-to-metal contact might be less than 5% of the total apparent surface area.
5%, that's insane. And what fills the other 95% of that space? Air gaps. Microscopic valleys filled with stagnant air.
And air is a notoriously terrible conductor of heat.
It's basically an insulator.
Yes. So whenever heat tries to travel across that bolted joint, it hits an invisible wall, a thermal bottleneck. The heat transfer rate plummets, and the temperature on the chip side of the joint skyrockets.
To mitigate this contact resistance, engineers use interstitial materials, right? They fill those microscopic air gaps with thermal grease, or they create bonded joints using brazing, soldering, or specialized thermal epoxies.
They try to bridge the gap.
And this is where the CAD model lies to you again. I want to use a home repair analogy here because it really drives it home. Applying thermal grease or solder is exactly like patching a hole in a drywall.
Okay, I'm listening.
You have two pieces of gypsum board that don't meet perfectly, so you take drywall mud, joint compound, and you pack it into the gap. You sand it smooth, you paint over it, and to the human eye, it looks like one single perfectly flat, continuous wall.
Right, it looks seamless.
But structurally, it is an illusion. You have introduced a completely different, weaker material into the system. The dried mud does not have the same structural integrity as the solid drywall.
That's very true.
When an engineer models a continuous metal connection in CAD, but the assembly floor actually uses a layer of thermal epoxy or a soldered joint, they haven't created a perfect thermal bridge. They have built a thermal dam out of drywall mud.
That is a highly accurate visualization. When two metals are brazed or soldered, the joint formed is not just the two base metals touching perfectly. The intense heat of the joining process creates a complex new alloy layer at the interface.
Oh, wow. So it changes the metal itself.
It does. And the thermal conductivity of that newly formed complex alloy is almost always significantly lower than the thermal conductivity of the pure base metals.
So even a weld acts as a bottleneck.
Even a weld. And even when using thermal grease, which is specifically designed to conduct heat better than air, the grease still has a vastly lower conductivity than the solid copper or aluminum it is squeezed between.
So you want the absolute thinnest layer of grease possible just to displace the air.
Yes, thin as possible.
But on the assembly line, someone applies it too thick, and suddenly your cooling paste becomes an insulating blanket.
Precisely. The thermal resistance of the joint creates a hard bottleneck. In high-power encapsulated avionics, this oversight is lethal.
Lethal how?
Well, the silicon die is generating massive amounts of heat, but the heat cannot bridge the contact resistance of the poorly designed solder joint to reach the heat sink. The encapsulant traps the heat inside the module. The local temperature gradient spikes violently, and the silicon literally cooks itself to death.
It just fries.
It does. The CAD model predicted a safe, steady-state operating temperature of 80 degrees Celsius because it assumed perfect conduction. But the actual physical unit on the test bench melts down at 120 degrees because the engineer ignored the microscopic reality of contact resistance.
It is always the invisible microscopic details that bring the massive systems crashing down.
Always.
Which leads us perfectly into our final and arguably most violent topic. Because when that heat gets trapped behind a thermal dam, things don't just gently stop working. They forcefully change shape.
They do. We're moving from thermodynamic theory into pure destructive mechanical force.
We are talking about thermal expansion.
Yes. The physical reality that the atomic lattice of almost every solid material vibrates more intensely as it absorbs heat, causing the material to physically expand in volume and contract when cooled.
And to quantify this destructive force, we use the coefficient of linear thermal expansion, commonly abbreviated as CTE, or denoted by the symbol alpha-1.
The defining mathematical relationship for CTE is straightforward. The fractional increase in length per unit rise in temperature. which is at the ratio of the change in length to the original length, is equal to alpha 1 multiplied by the change in temperature.
So it tells you exactly how many micrometers a 1-meter bar of material will stretch for every single degree it heats up.
Exactly. The units are reciprocal temperature, usually expressed as micrometers per meter Kelvin, or simply 10 to the negative 6 per Kelvin.
Right.
Over small, everyday temperature ranges, this expansion is roughly linear and proportional to the temperature change. However, for precision engineering, you have to be acutely aware of which definition of CTE your software requires.
The sources are very specific about this trap.
Yes, they are. There is the true coefficient of thermal expansion, which is the exact mathematical slope of the tangent line at one precise temperature point. And then there is the mean coefficient, which is the average rate of expansion over a broad temperature range.
And software cares which one you use.
Deeply. Finite element analysis software like Nastran specifically requires the mean CTE to be input for the specific temperature range your part will experience. If you input the true instantaneous CTE from a textbook table at room temperature, but your part operates at 400 degrees, your stress models will be wildly inaccurate.
But how do we even measure something that small? We are talking about metal expanding by a fraction of a hair's width.
It requires extreme precision. The most common industrial method is mechanical dilatometry.
Dilatometry.
Yes. A test specimen is placed in a highly controlled furnace. As it heats and expands, the physical displacement of the ends is transmitted via non-expanding push rods to a highly sensitive sensor.
So it physically measures the growth.
Exactly. For slightly more precision, we use thermomechanical analysis, or TMA, where a delicate probe transmits the microscopic length changes to an electrical transducer. TMA is the standard for measuring CTEs down to about 5 times 10 to the negative 6 per Kelvin.
But if you are working on, like, space telescopes or military lasers, and you need to measure materials that barely expand at all, you have to use light itself.
Correct. You use optical interferometry. This measures the physical displacement of the material in terms of the number of wavelengths of monochromatic light that shift as the material grows.
That's amazing.
It is incredibly precise, perfectly suited for engineered low-expansion materials. However, because it relies on bouncing light off the optical reflectance of the material's surface, the method degrades and becomes largely unusable once the furnace hits around 700 degrees Celsius and the surface begins to oxidize or blow.
So let's talk about the materials themselves, because the physical differences between metals are staggering, and that is where the disasters happen. The sources highlight engineered low-expansion alloys, things like binary iron-nickel alloys, famously known as INVAR.
INVAR is fascinating. It's engineered specifically so its dimensions do not change appreciably with normal temperature swings. The atomic structure is designed to absorb the thermal energy without expanding the lattice.
It just eats the heat without growing.
Exactly. These materials are crucial for precision applications where microscopic warping would ruin the machine. We use them for rods and tapes in highly accurate geodetic surveying, for the compensating pendulums and grand clockwork, for the structural mounts and optical laser measuring systems.
Wow.
And crucially, for the massive vessels and piping used to transport liquefied natural gas.
Oh, right, because liquid natural gas sits at roughly negative 160 degrees Celsius. If you used standard steel piping for that, the thermal contraction when you pump the cryogenic liquid in would physically rip the pipes off their mounts.
Exactly. It would shatter. And on the complete opposite end of the thermal spectrum, we have aluminum.
Aluminum is notoriously expansive.
Highly expansive. Its dimensional change is roughly twice that of standard ferrous metals like iron or carbon steel. The average CTE for commercially pure aluminum is massive, roughly 24 times 10 to the negative 6 per Kelvin.
And that extreme difference, aluminum wanting to grow rapidly and steel wanting to stay put, that is the root cause of some of the worst mechanical failures on the shop floor.
Without a doubt.
When you try to force high expansion materials to coexist with low expansion materials, physics always wins.
When you bolt, rivet, or permanently bond these differing materials together and the assembly heats up, the aluminum tries to grow twice as fast as the steel holding it. The steel acts as a physical cage, restraining the aluminum.
Which creates stress.
It generates immense, incalculable internal mechanical stresses.
Let's walk through two fantastic real-world examples of how engineers are forced to design around this reality rather than fight it. The first is heavy shipbuilding. Modern naval architects want to lower the center of gravity of large ships, right? So they build a massive heavy lower hull out of high-strength steel, but they build the towering superstructure, the bridge, the crew quarters, out of lightweight aluminum.
A logical choice for weight distribution, but a thermal nightmare.
Exactly. You cannot just weld that massive aluminum block solid to the steel deck. As the ship sails through the freezing North Atlantic and then into the blazing sun of the equator, that massive aluminum structure is going to expand and contract violently.
The forces involved are astronomical.
If it were welded solid, the thermal expansion forces would literally tear the aluminum bulkheads to shreds or rip the welds right off the steel deck. So engineers have to design complex sliding slip joints.
They have to let it move.
Right. They use specialized plastic caulking, explosive transition joints, and mechanical stress-relieving devices, so the entire aluminum building can physically slide back and forth over the steel framework by several inches without ripping the ship apart.
It requires visualizing the ship as a dynamic moving organism, not a static block of metal.
Right, it breathes.
The second classic example happens thousands of times a minute inside your car. In an internal combustion engine, the pistons are subjected to explosive heat. To save reciprocating weight and allow the engine to rev higher, the pistons are cast from lightweight aluminum.
Okay, aluminum pistons.
But the engine block itself and the cylinder walls the piston slides against are usually cast iron or steel to handle the explosive pressure.
Which is a recipe for disaster. As the engine fires and comes up to operating temperature, that aluminum piston is absorbing massive heat and trying to expand radially twice as fast as the iron cylinder wall surrounding it.
Exactly.
If left unchecked, the piston would rapidly expand until it jammed tight against the cylinder, seizing the engine instantly and throwing a rod through the block.
To prevent this catastrophic seizure, automotive engineers have to fight the thermal expansion with highly clever mechanical design. They will cast low-expansion iron cylinder linings into the block.
Okay.
Or, more ingeniously, they will design pistons with split skirts or cast rigid, non-expanding struts made of invar or steel directly into the core of the aluminum piston.
Oh.
These internal struts act as a physical skeleton, mechanically restricting the aluminum's growth in the critical outward dimensions. They force the expansion to happen in harmless directions, like up toward the valves rather than out toward the cylinder walls.
That is brilliant. But the ultimate nightmare scenario, the ultimate shop floor pain point that ruins careers, is when you don't have the luxury of slip joints or internal struts. When a young engineer attempts to permanently atomically fuse two fundamentally different metals together.
Yes.
We were talking about the terror of welding dissimilar base metals.
This is where metallurgical reality forcefully overrides CAD models. The coefficient of thermal expansion is the absolute non-negotiable critical factor when welding dissimilar metals.
So give us an example.
Let's examine a very common, very dangerous application found in high-pressure energy conversion plants. Welding an austenitic stainless steel pipe to a plain ferritic steel pipe.
Okay, austenitic stainless steel, like your standard 304 or 316 grades, has a completely different atomic crystal structure than plain carbon ferritic steel.
Yes, it does.
Because of that face-centered cubic structure, the sources note that austenitic stainless has an expansion coefficient roughly 1.5 times higher than ferritic steel.
Let's walk through the physical mechanics of the weld. The welder strikes the arc. The intense electrical heat melts both the stainless steel and the carbon steel into a liquid weld pool at thousands of degrees.
Sounds normal so far.
In that liquid state, everything is fine. The metals mix, they form a joint, but the second the arc is removed, the joint begins to cool and solidify.
And the atomic tug-of-war begins.
Viciously. As the temperature drops back toward room temperature, the austenitic side of the joint desperately wants to shrink rapidly because it has a high CTE. It wants to contract by a large volume.
But it can't.
Right, because it is now atomically locked to the ferritic side of the joint, which has a much lower CTE and is shrinking at a much slower, more stubborn rate.
They are permanently fused, but they are fighting each other with the force of thousands of pounds of pressure as they cool.
The differing CTE values induce massive opposing forces. The fast-shrinking stainless steel experiences extreme tensile stress, a violent stretching, tearing force, because the slower ferritic steel is holding it back.
And the other side.
Conversely, the ferritic steel experiences massive compressive stress, a crushing force. If the weld procedure is not meticulously engineered to account for this, using specialized filler metals like Inconel or controlled preheating, the metal subject to the tensile stress will simply rip itself open right down the center of the weld bead while it is still cooling on the table.
Wow.
This is called hot cracking.
You literally watch the weld cool, and a jagged black crack just unzips right before your eyes. But the scariest part is when it doesn't crack immediately.
Yes. Sometimes the weld survives the initial cooling process. The internal stresses are locked inside the metal, completely invisible to the naked eye. The pipe is installed in the power plant.
Ticking time bomb.
Exactly, because in a power plant, the pipes experience cyclic service. The plant powers up, pumping superheated steam at 600 degrees through the pipe. Then the plant powers down at night, and the pipe cools back to ambient.
Every single time that plant cycles, that welded joint is violently expanding and contracting. The stainless side pushes harder, then pulls harder.
Yeah.
It is microscopic bending back and forth every single day.
That alternating expansion and contraction inevitably causes severe metal fatigue. The locked-in residual stresses from the mismatched CTEs magnify the fatigue damage. Months or even years later, the joint simply gives up. You get cold cracking in service.
And then, boom.
A high-pressure steam pipe violently shears apart at the weld, causing a catastrophic plant shutdown, or worse, a fatal industrial accident. And the what cause analysis will trace the failure entirely back to an engineer in an office who specified a dissimilar metal weld without respecting the different thermal expansion coefficients of the materials.
It is all incredibly dangerously connected. The thermal heat we fail to convert to useful mechanical work because of the second law's unavoidable entropy tax. That wasted heat gets dumped into the physical casing and the structural joints.
It all cascades.
Those joints have microscopic imperfections and thermal contact resistance, acting like physical dams, trapping the heat in localized pockets. That trapped heat causes the atomic structure of the metals to expand. And because different metals expand at different rates, that thermal expansion creates massive internal shearing stress that literally rips the atomic bonds of the welds apart.
It really is incredible.
The entire machine, from the massive turbine blades down to the microscopic solder bunks, is one delicate, highly stressed balancing act against the laws of physics.
It is one continuous, unforgiving thread of energy management.
Before we wrap up, I want to hit a few of the most popular, painful questions young engineers are asking about this exact subject online right now, because the textbook theory clearly isn't answering them.
All right, let's hear them.
Question 1. I ran a massive, highly detailed 3D CFD simulation on my new compressor design. The computer says I should get 92% efficiency. The physical test rig on the floor is only hitting 84%. Why is the computer lying to me?
The computer is not lying. It is only answering the exact question you asked it, based on the parameters you provided.
So what's the missing parameter?
The most common reason for this massive discrepancy is that CFD models often grossly undermesh the boundary layers near the metal walls to save computing time, effectively ignoring the true scale of the friction. Furthermore, a fluid simulation only measures the aerodynamic efficiency, the isentropic efficiency.
Oh, it ignores the mechanical side entirely.
It completely ignores the mechanical losses.
Yep.
Your CFD software doesn't know about the physical friction of the journal bearings supporting the heavy shaft, or the aerodynamic windage drag of the spinning discs in the cavity, or the energy required to drive the oil pumps. You are comparing an idealized fluid model against a physical machine burdened by mechanical entropy.
Question 2, and we see this constantly in the PC building and avionics space. My encapsulated chip is running too hot. Can I just use a much thicker layer of premium thermal paste to lower the contact resistance and pump more heat into the sink?
Absolutely not. That is a fundamental misunderstanding of what thermal paste does. Thermal paste, even the most expensive premium brand, has a significantly worse thermal conductivity than the solid copper or aluminum of your heatsink.
Right. Remember the drywall mud?
Exactly. Its only purpose is to be slightly more conductive than the stagnant air trapped in the microscopic asperities. You want the absolute thinnest, most translucent layer possible applied under high pressure purely to displace the air gaps. If you apply a thick layer, you are no longer bridging a gap. You are building a physical wall of low conductivity paste. You will insulate the chip and cause it to overheat faster.
Final question. I'm trying to figure out if I need to run a complex transient thermal analysis on my component. How do I know at a glance if I'm dealing with a low Biot number situation where I can just use the lumped capacity assumption?
Look at the physical properties of your materials and your environment. A low Biot number requires high internal conduction and low external convection.
Give me a visual.
A classic example is a small block of pure copper sitting in completely still, stagnant air. Copper transfers heat incredibly well internally, and still air is terrible at pulling heat away. That block will heat up uniformly. That is a low BO number.
And a high Biot number.
A high Biot number is the exact opposite. Imagine a block of insulating plastics immersed in a roaring river of freezing water. The water strips the heat from the surface instantly, but the plastic's internal resistance prevents the core's heat from escaping. The surface freezes while the core remains hot. That is a high Biot number, and you must run the complex internal gradient math.
Physics does not care about your spreadsheet. Which brings us to the end of today's incredibly deep dive. Let's recap the journey we took today.
It was a long one.
We started in the perfect, idealized world. We established the baseline gatekeepers of the universe with the continuity equation's mass bottleneck and the massive energy ledger of the first law of thermodynamics. We forced that high-speed fluid to do work on spinning blades, exploring the brick wall of stagnation enthalpy, Euler's momentum transfer, and the chaotic currency exchange of Rothalpy.
Then we introduced the brutal reality of the shop floor, the second law of thermodynamics, and the Gouy-Stodola theorem, which proves mathematically that entropy generation is the universe's unavoidable mob tax, physically manifesting as heat and vibration to steal your mechanical work.
We looked at how that lost work destroys efficiency ratings, specifically the massive accounting fraud of using total-to-total efficiency when your exhaust kinetic energy is actually blowing uselessly into the atmosphere, and why you must use total-to-static efficiency to avoid a lawsuit. We zoomed down to the microscale, looking at the Biot numbers tug-of-war and the myth of the perfect CAD joint, seeing how the microscopic drywall mud of thermal contact resistance acts like a thermal dam in delicate avionics. And finally, we saw the physical, violent consequence of that trapped heat. The metal-tearing forces of thermal expansion, the differing CTEs of aluminum and steel, and the severe explosive dangers of hot and cold cracking when foolishly welding dissimilar metals.
It is a massive amount of interconnected material, but understanding how the thermodynamic theory physically manifests as mechanical destruction is what separates a student taking an exam from a working engineer keeping a plant online.
Absolutely. And I want to leave you, the listener, with a final provocative thought to mull over as you head back out onto the floor. We just established that entropy generation is the ultimate, unavoidable tax on all our mechanical designs, and that thermal expansion introduces microscopic tearing stress into every single bolted or welded joint as temperatures fluctuate. Knowing that the universe is actively degrading the system at all times is the concept of a steady-state machine, actually just a convenient lie we tell ourselves to make the math easier. Next time you look at a perfectly running piece of heavy equipment humming away on the shop floor, ask yourself what hidden microstresses, microscopic air gaps, and trapped heat gradients are actively trying to tear it apart right now.
A sobering but absolutely necessary perspective for any designer.
If this helped you even a little, please tell us. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing instead of just talking into the void. We are excited for your feedback, negative or positive.